Hmm? Hmm. In the last video I talked about binary addition and subtraction, and how subtraction we use the ones complement and the twos complement to get the results. In this video I'm going to actually show you some of the circuits that we use to do addition and subtraction. And the one that you are looking at right now is called this is an adder circuit. The adder circuit is actually made up of two components, or two groups, formed from a half adder and then two half adders put together to make a full adder. This adder circuit consists of one half adder and three full adders. So a half adder is always used to add the least significant bit, and that's this section right here. This is a half adder, and it consists of a XOR and an AND gate. And the XOR gives us the sum, the AND gate gives us the carry out, and we always have to have a half adder to do the least significant bit. You notice that it doesn't have any provisions for a carry in. Well, in the least significant bit, we never will have a carry in, so it doesn't need one. Well, every bit above that does need a provision for a carry in, so we have to expand the circuit a little bit. And we do that by creating a full adder. A full adder is nothing more than two half adders put together. So here's a full adder in that block. And notice that we have a half adder here and another half adder here, and what would have been the carry out from these two goes into a OR gate and forms the carry out for that, for the next stage. The way this circuit would be set up, for example, let's say if we had 7 or 8 bits, and we needed to add 8 bits to 8 more bits. Well, for the least significant bit, for the LSB, we would need a half adder. And this is always going to be true. We're always going to need a half adder for the LSB. For every bit above that, we're going to need a full adder. And if we have 8 bits total that we need to add, the half adder will take care of 1 bit, so we'll need 7 full adders to take care of the rest of the circuit, which means we have to build 7 of these circuits to perform that function. And you can see it gets pretty big fairly rapidly. One of the things that is as a drawback to this circuit is that it acts like a ripple adder. Well, it is a ripple adder. The subsequent circuits all require a carry in. And imagine then that we add 1 and a 1 and we get a carry, and there's more carries coming through here. This carry has to ripple from one stage to the next before this stage can finish its function. So we start here, we ripple through this one, the carry out comes in, carry in, it ripples through, and so on. So this circuit isn't really suitable for very high speed work, but it's a perfect example to talk about how the circuit works as far as its basic functionality. Let's go ahead and do a simple addition problem with it, and see how it works out. So we have some numbers that we're going to come up with, and we'll keep them relatively simple. So 0, 1, 0, 1, and we'll do that. So this is going to be these are going to be our A's, so that's going to be the top level. That's the AUG end, and then the lower, that's the B's here, and that'll be the add end. So let's go and put those values in there. So we end up with 1, 0, 1, and we have a 0 here, and we're going to add that to 1, 1, 0, 0. And here's how the result would be achieved. So we know we have an XOR gate, like inputs would give us a low. 1 and a 1, that's going to give us a carry out of 1. which is going to feed into the next gate and into this AND gate. A 0 and a 1, we're going to have another 1. A 1 and a 1 will give us a 0 for some 1. The 1 comes into this gate, and we have a 0 and a 1 here. It gives us a 0. That gives us a 1 on this AND gate. As soon as we have a 1 into the OR gate, we get a carry out of 1. We have a 1 here and here as well. Another 0 and a 1 gives us a 1. A 1 and a 1 is a 0. And this 1, 0 comes in, gives us a 0 out. And I have a 1 and a 1 here, gives me a 1. And again, I have a 1 for the carry out. I have a 1 here. And a 0 and a 0 are going to give me a 0. This 1 feeds here. This 1, 0 feeds there. 1 and a 0 give me a 1. A 0 and a 1 give me a 0. A 0 and a 0 here give me a 0, 0 here with an output of 0 and a final carry out of 0. The carry out is always going to be our most significant bit. In this case it's 0, but I'll write it down. So we have a 0, and then we have a 1, a 0, a 0, and a 0. So according to this, our answer is in binary is 8. And if we go through this, we can see that 1 plus 1 is 0, carry the 1. 1 and 1 is a 0, carry the 1. 1 plus 1 is 0, another carry of 1. And the answer is match, so this adder works quite well. Well, what if we want to do subtraction? We can't do it with this circuit, but by making a few modifications to it, we can come up with this. This is a subtractor circuit, and guess what? It consists of a half subtractor, which is this section here. The half subtractor consists of that XOR gate, an AND gate, but now we add an inverter to the A0. This gives us a complemented value. And the half subtractor is always used to work out the solution for our least significant bit. Notice that it doesn't have a borrow in. Since we're doing subtraction, we may have to borrow. Well, you're never going to have to borrow from the least significant bit. And the following circuit, so for every bit after that, we're going to need a little bit different schematic or construction, because now we're dealing with carries. So now we have to have, guess what, a full subtractor, and the full subtractor is going to be made up of 2 half subtractors. So here's one half subtractor, here's the other half subtractor, and or the result, and this in total gives us a full subtractor. And again, for every bit above the LSB, we're going to need a full subtractor to do the work. So if we had a 16-bit number that we were trying to work with, we'll need 1 half subtractor and 15 full subtractors. And this circuit will, when the outputs are negative, will give us a 2's complement answer. So I'll work through a couple of these, and we'll take a look at its function. And let's select some numbers to work with. And this will be our start. And obviously, this is going to give us an answer of 4. So we put our values in there, and this is going to be our A's, and this is our B's. And I'm going to subtract 4. And we'll just work straight through the circuit. And this is going to be our least significant bit, the difference of 0. And our borrow out will be our most significant bit, if we have one. And here's our solution. So according to our values here, I should have a 0, that's the most significant bit, a 0, a 1, and then 2 more zeros. And here's our 1's place, our 2's place, and our 4's place. So indeed the answer is binary 4, and it works out quite well. So let's see if we end up with a 2's complement output if the number is negative. And we'll just put in some set of values, make it a subtraction problem. So according to the outputs on this circuit, our answer is, with the borrow out being the most significant bit, 1, 1, 0, 1, 0. And we started with up here with 4 minus 10. So our answer should be negative 6. And we want to find out if this is the binary value for negative 6. And the way we would do that was we 2's complement it. So we complement all the values. And then we add 1 to that complemented value. So 1 plus 1, 0, carry the 1. And there's our 6, so the answer is right. This answer is equal to negative 6. It's rather inconvenient to have to build 2 circuits to do, one to do subtraction, one to do the addition. So what can be done is we can combine the 2 circuits that we had and make a circuit that becomes a adder and a subtractor. And that is what this particular circuit does. Notice that this section is a adder. But now we've got a sum and a difference output instead of just a sum output. The difference with the circuitry is that I've added exclusive OR gates to one of the inputs, in this case all the B values. And what these exclusive ORs will do is they will either complement or leave the value as is depending on the voltage that I put into them. When the switch is grounded, this circuit acts just like an adder. So when I ground this, I'm going to put a 0 on every one of these inputs. And let's say that the value on the B's was 1, 0, 0, 1. The exclusive OR gate, if the values are different, the output is a 1. If the values are the same, the output is a 0. And it's a 0, and there's a different, it's a 1. And notice that the outputs of these exclusive OR gates are exactly the same as the inputs. Now, if I take this switch, attach it to VCC, which means that now I put a 1 on every one of these. Well, a 1 and a 1 gives me a 0. A 0 and a 1 will give me a 1, and again, and a 0. And notice now that the outputs from this gate are the complement of the inputs. So let's try a subtraction problem and see how that works out. The addition problem, I think, if the values are exactly the same, it's going to work the same as the previous circuit. So a subtraction problem of some value. So we'll try this for a subtraction. And here's my A's again, and here's my B's. And because I'm doing subtraction, I attach it to VCC, so every value on this pin is going to be a 1. So the answer then is, again, the borrow in being the most significant bit, 1 0 0 1 0. Our original value was 11, and we're subtracting 8, so the answer should be 3. Well, this does not look like 3, but remember that in the ones complement in the circuitry, we have to do an end around carry if that most significant bit is a 1, and indeed it is. So we have to do an end around carry, so we have to bring this number around and add it to the result, and that is binary 3. As I mentioned before, one of the problems we can have with a circuit like this is that these sums and differences, they have to propagate through the entire circuit sometimes, and that'll slow things down because this result then has to wait for something that's happening up here. So we end up with propagation delays through each one of these stages. What we want to do is try to eliminate those problems by having the circuit actually look for the carries at the same time it does the addition. And that is done by a circuit like this. This is still an adder, but this section in here is what's called a carry look-ahead group, or just a clag. Carry look-ahead group probably sounds better than clag. But what this will do, at the same time that it's looking for, it's doing the addition problems, it's also taking the outputs of these and feeding any possible carries to the stages that come above. There's an entire video to be done just on carry or look-ahead groups. But notice that one other thing, there's a carry in to this least significant bit. Now, if you're only doing 4 bits, you can ground this input. But what you can do with this circuit then is you can hook up 2 or 3 or 4 of these, and they will do, you'll have a carry in then from the carry out of the last stage. So ground it for the first stage. You won't need it for the least significant bit. But if you have another circuit, you want to add 8 bits, you would build a circuit similar to this, put it down below, and then the carry out would go to the carry in of that next stage. You can see how the complexity of this circuit goes up quite a bit. What it does now is it shortens the path to these outputs, so we don't have to wait for a ripple effect to occur from the carry out of this circuit into the next adder, into the next adder, into the next adder. The carries are instantly put here. And what this does, it'll double, at least double the speed of the circuit that you're working with. So that's a carry or look-ahead group. This is the adder subtractor circuit that we just went over. And instead of using a switch, I'm using a wire, which I can move between ground for adding and VCC for doing subtraction. So nice, simple wire. These are my A values, so A0, this is my least significant bit to the most significant bit. My B values, least significant to most significant, and then my LEDs to give me an output. So as an adder, it should just give me a straight value. So if I put in 4 and add 4 more, I should end up with 8. So 1s, 2s, 4s, and 8s, and I have an 8 value. If I added 2 more to that, I should now have a 10, and so on. And so now I have 8 and 4, I have a 12, so 6 plus 6, and the answer again is correct. Now, one of the things about this circuit is that when I make it subtract, the first thing you'll notice is that when I put it back on 0, all of the LEDs are on. And you'll recall that there are actually 2 zeros in the ones complement system. And this is going to be a ones complement system because once I put this into subtraction, all of the values on the A's are going to be complemented. And when I complement the values, everything here becomes inverted. So this is actually a 0, but it's the negative equivalent of 0 because all of the LEDs are on. If I complement this, it becomes 0, 0, 0, 0, and 1, and I throw out that most significant bit. let's try a straight number that doesn't give us a negative answer. And in this case, let's try 8 minus 3. And you'll note that, well, this does not look like 8 minus 3 does not look like it should give us this value of 8, 4, and 2, a 10. But because this complements all of the values, what we have to do is actually take the opposite of these outputs. So we have actually a 4 and a 1, which is 5, and that is the right answer for 8 minus 3. Let's give it another shot. Let's try Let's try 7 from 6. So here's 7 on the top. So this is the indication for 7. And I'm subtracting 6. And of course 7 minus 6 is 1. And because this is a complemented output, this is the actual bit we would look at as being the one that indicating a 1. So it's 1, 0, 0, 0. And you can see, even though it's a little bit confusing, that the answer is, as long as you remember to complement the answer when you're doing subtraction, it'll come out properly. But what happens if we use a negative number? Well, in a negative number, this circuit is a little bit peculiar in that we have to do an end around carry on a negative, which is not something we normally do. So again, let's leave this value on 6, but now let's subtract 14. So we have an 8, a 4, and a 2, so there's our 14. And here's our 2 and a 4, and that's 6. So 6 from 14 should give us negative 8. And notice that this is just showing us 7. But if we take this most significant bit right here and do an end around carry on it and add it to the circuitry, we would actually have an 8. And notice now we don't have to do the 2's complement, but we have to do the end around carry. So on negative numbers on this particular device, do the end around carry and add it to the values that are actually high. Let's try one more to see if we can clarify that a little bit more for you. And we'll put everything back onto 0. And this time let's try 9. And we'll subtract that 9 from value of 5. So here's my 5 and here's my 9. And of course 5 minus 9 is 4. Notice that only 3 is showing, so we take this bit, do the end around carry on it, add it to the 2 that are shown as being high, so we have a 1, 2 plus 1, and that gives us the 4. And the end around carry system seems to work on this device effectively. Now, I don't want to leave you with the idea that every time that you have to do addition or subtraction, you have to build something as complicated as this or as that carrier look-ahead group device that we saw earlier. You can make a adder out of a discrete IC. You don't have to make them out of all those XOR gates, AND gates, and OR gates, and inverters. You can make a device, make it out of a dedicated adder device. This is a 7483. It's a very simple and very old adder. And remember, we're dealing with primitives in these videos. So yes, I can do all of this stuff with programmable logic, but the point is to understand the digital logic behind it and try to do eventually some troubleshooting on this. So again, it's a 7483. It's a 4-bit adder, and this is my display. So it's a LED bar graph. And this is my 1s, my 2s, my 4s, and my 8s, and I didn't need to use the rest of them. And instead of putting resistors individually on each one, I made a little carrier, and I put a bunch of 470 ohm current limiters on there so I can just use it in one package. And here's my A's, my A0 up through my A3, so my 1s, 2s, 4s, and 8s, and here's my B's, 1s, 2s, 4s, and 8s. So if I were just to add 8 plus 4, I should get 12, and you can see that the 12 is showing. And I continue. If I do 8 plus 12, and now you can see that I have 1s, 2s, 4s, 8s, 16, so I have a 16 and a 4, so I have a 20. And let's say I do one more. Let's do 7 plus 5, and that should give us 12. Add 2 more to that, and I get 14. Add 8 more to that, and then I should get 22. So 1s, 2s, and 4s, and 8s and 16s. So it's 16, a 4, and a 2, and I get 22. And remember, you don't have to build a huge circuit to do addition and subtraction. There are some really great ICs out there. The 74383, I believe, is one of them. It does it's actually an arithmetic logic unit. Does a lot of work for you. And again, these are all primitives, so you should be able to find something more up-to-date and modern. But again, for learning troubleshooting and wiring, these are inexpensive and they work great. They have a long proven track record.